I'm Dan Sweeney from MathSpec. In the part 1 video, I discussed acquiring and preparing your data for SPS. In the second part, we launched an EC2 compute unit on Amazon AWS and processed some data files on it. Now in this final video, I'll go through importing the results into a Microsoft Access database. Microsoft Excel is a very widely used spreadsheet application that most people are familiar with. Microsoft Access is less commonly used, but it has many features in common with Excel, and so it's easy to use if you are already familiar with Excel. When we finished the part 2 video, we had transported over from the cloud EC2 server to our local computer, and these are the four summary files and a Access database template that we need to start the Access database. I'm going to open this up, and it's going to ask me to name this file. I'll try to put it in the same folder. So let's call it SPS data. Okay, we'll save that. So when it prepares the template, basically it's set up 4 tables and 8 queries, and they're all empty right now. So the first thing we need to do is import the data from file, text file. These are our results from the SPS on AWS were comma separated values. So those are the files we're going to import here. It'll start with the ISCID. You can go in any order you want. Now it already kind of has detected that it's comma separated values. Okay. Another file. The next one, process data. And we're appending the data to the table. So if you do another run and another run, you can keep using the same table. It's very helpful to just make this database larger and larger. This is the largest table. And the last one is a summary of all data. Okay. Okay, so we've imported all the CSV files from that we had gotten from SPS, and now they're in these tables. Now once the tables are formed, these 8 queries are already activated. You don't have to do anything unless you want to create a new query. But there is one other thing we need to do to set up this database. When we subtract blanks, it's actually subtracting from the process data folder or table here, and the screening results still have possible identifications for blank compounds, and we want to get rid of those. There's a easy way to do it, and it's a query analytes in blank to remove from the screening results. Let's go to home and select all, and then delete. So I'm selecting everything in that table and deleting them. And the reason is later on, if I say, well, let me look for pharmaceuticals or flame retardants, I don't want to find possible hits that were in the blank. I just want to see what's in the actual samples. So I can close this query. Let's go to process data. It's going to be by retention time. It's sorted by retention time. I prefer to sort by mass. Okay. Now I thought I would just pick out contadine. Okay, let's try this one. It has an accurate mass of 176.0947. Now, this is the data. The precursor was 177.1020. So these numbers are what was in the actual spectrum. It saves the 11 largest fragment ions and the precursor ion. But then to get the accurate mass, it determined in this case that it was a protonated adduct, so it subtracted the mass of a proton. So this should be very close to the the exact mass of contadine. So I can, okay, I should mention that a column in Access is a field. So these these are all fields that are searchable. And a row is a spectrum. A row is a record. It's considered a record in a database, but each record is a separate MS-MS spectrum. So this particular spectrum was recorded at 2.9 minutes in a run of River F. And this is the intensity at the time, the intensity of the precursor ion at 177 when this precursor was selected for MS-MS. And it wasn't at the maximum of where that analyte peaked in that sample F. That was at 37,050. So the SPS software searches the area around 2.91 minutes, and it records both the intensity when the MS-MS was taken and also what was the highest in that region. This is, again, this is the accurate mass. The adduct, there can be sodium, potassium, ammonium, and if it's a sodium or potassium, you'll see the actual mass of the precursor, but it will subtract that out to get the accurate mass of the compound itself, the analyte. The next table, or the next field, is a link to the EPA Comtox Chemicals dashboard. If we click on that, it will go into the dashboard. It'll find any compounds in the EPA Chemicals dashboard within 4 millidaltons of the accurate mass. So here's a bunch. There are 367 compounds within 4 millidaltons of that accurate mass. This is also nice. You can sort by how many sources you have. So for example, catenine has 155 sources, so that makes it maybe a little more relevant than some of these other compounds. But there are quite a few compounds within 4 millidaltons of that accurate mass. Now the next 12 fields are, these are the actual experimental accurate masses of the 11 of the fragments, and then we always have the precursor ion mass as the 12th one or the last one, because you may not always have 11 fragments that are over 1% in intensity. After the masses, these are the relative intensities. Now this is on a scale of 1 to 100. I know some instruments do 1 to 999, but these are all converted into relative where the maximum is 100%. And then these are the isotopes ratios, and this is the experimental isotope ratio. So for this particular analyte, it appeared to have 8% on the second isotope and 4 on the first isotope was 8% and the second was 4%. And the run name is whatever sample name it was given before the run. Now this column, the primary text, this is a relational database, and the nice thing about relational databases is you don't have to put the same information in multiple times, and also you don't have to have a table that goes on and on. So it's sometimes easier to have two tables, and this is a link between the process data and the screening results. And then the last field is actually it's a text string, and it attempts to give every analyte a unique text label, if you will. So if we go back here, you can see there's a break between 27 minutes and roughly 3 minutes. So these are definitely not the same compound. But if we go and take all the ones that have that mass and a retention time around 3 minutes, they should all have hopefully all have the same analyte name. So we can if we do another run, we do have a way using that unique analytes output to always keep catenine at with this particular name. Now the relationship between the two tables, if you click on this plus sign, it will go to the screening results and bring up compounds that may match, if you will. So this, I need to scroll this down. So there's a very large number of compounds in PubChem that, because some of these scores are pretty good, even though, but there are a number of them. So if we look at the first 5, it turns out that these are basically the same compound in PubChem, but for example, catenine can have different, there's a asymmetric carbon in there, so you can have the R and the S forms, and you might have a salt. So the one with the most synonyms is this one. So it's hyperlinked to PubChem, and we can also, for example, if we go to chemical and physical properties, that'll give us that the exact mass is 949. We can compare that to what we have. Let's see, it was 947 for this particular spectrum. And so these are all pretty much the same, but they may be, for some reason, getting a different number. Okay, so let's go back to the database, and if we go into screening results, we can look at this separately. And for example, we could look at classes. So let's say we want to see flame retardants, or maybe fungicides. Let's look at fungicides. So these compounds, now there are 240,000 compounds in the screening database, and less than 20,000 have been assigned to a class. So the most common class that you'll find is not classified. But we can do this, and then we can look for particular types of compounds if we need to do that. Okay, let's go back here. Let's look at these different tables. Now, summary of all data. This one, it looks very much like, I'll sort it again. It looks very much like the other table, except this has got 41,000. This is the entire data for the run that we did on SPS. So there were 41,625 spectra, and now each one is a separate row. Whereas the process data, after we subtracted out the blank and ISCID fragments, which I'll talk about in a second, we only have 20,000 spectra left. ISCID, this is in-source fragmentation. So during the process, even though it wasn't deliberate to do fragmentation in the source, it always happens. And the DDA compute unit may choose ISCID fragments rather than, let's say, the whole compound. So these are compounds that have been assigned as fragments, and we have, if you will, if you have a fragment, let's see if we can find something. Like here's a 394, and the fragment is a 172 that it picked up. So if we have, and we would have 394s that have this fragment, we can also see the MS-MS spectrum of the fragment itself. So in a way, it's MS to the third on a, this was done on a QTOF. So those are the four types of tables that we have. Now the queries, we already used one to get rid of compounds that were in the screening results that were from blanks and samples that had those blank components in them. We can look at controls, and what I did was if we go to sample name, I changed river A and river E. I added the words control in there, and it shows you don't need to have all small letters or big letters or whatever. So any string of CONTROL will the query will separate those out from the rest from the process data. So we have 1,128 controls. And then if we look at test samples, these are the remainder. So if we had 19,000 that are not controls and 1,128 that were controls, those should sum up to the number of compounds or analytes in the process data. Now, we could, I'm going to stretch it out a little bit here. We could have test samples. Let's say we're looking for a metabolite. We can say, well, these are test samples that did not have any corresponding analyte in the control. So this is absolutely not showing up in the control at all. But now sometimes you might say, well, the test sample, there might have been a little bit in the control. Maybe it's an impurity or a degradation product that's in the, let's say, the drug, and it is being detected, but the test sample has much more. Let's say, and in this case, we've set it at a factor of 10. So we can click on that. So these are where there is the same analyte is in both the sample, the test sample, and the control, but in the test sample, it's 10 times higher. Now, the nice thing about queries is you can also, we can view the design of this query, and you can see that the factor for whether it's greater or not, we set it at 10. Now, we could have been more conservative and set it at 5, let's say. You can change that if you like. So there's a lot of flexibility with the queries. Okay, so let's go back to the regular view. Now we could have some controls if we're looking at up and down metabolism. Maybe there's some controls that had a certain metabolite, let's say a normal metabolite, but because of the treatment with a drug or pesticide, that metabolite has dropped. So these are controls that have a greater maximum intensity than the test samples. There's another query that is sometimes useful. Find all records with a particular fragment mass. I'm going to use 201.046, and you have to put the fragment mass in twice. Okay, and now it's saying that, for example, the 388.1548, go in here. So it's this particular analyte, and the compound, I know it's cetirizine. It's a pharmaceutical. And the 201 piece that I'm searching is basically this piece down here, this benzyl. It's a diphenyl benzyl. There's a couple, there's a 404 150. Four 150, and actually there are two in there. This one was at about 17.3, so it's the second one here. Okay, so if we look at that, it says this one's a metabolite, and it's a cetirizine N oxide. So again, it has this piece here, so we can find some related compounds. Now the other one, this one is also, it's coming out sooner. And what we could right click and copy these two records or these two mass specs, and then go into Excel and do a paste special with the Excel 8.0 format, and then make sure that we have 4 decimal places. And we can also then copy those. And we can transpose it. We could then import this into, if we open up the Excel add-in, we can copy these masses and intensities. This one would probably be better. These intensities are awfully small with the lower energy. And we could get some more data on this 404. So we have other videos on using the Excel add-in. The last query that I'd like to show is exporting. So let's say this is the first time we've run this type of sample and we want to collect all our data in this database. Well, the next time we run, the accurate masses will probably vary a little bit and the retention times are going to vary. But hopefully we'd like to get the same analyte numbers. But those, when you create a new database, that's the first time those are seen. But if we are going to continue to add samples, we would like to use this query. And what this does is it looks at the string, if you will, analyte string, and it also stores the average mass and average RT and how many times it's seen it. So we bring up this particular query, and then what we want to do is export to Excel, and let's call it that format. Okay, and let's just call it unique analytes. That's the name that we would like to use. Export with data formatting and layout. I don't want to save the steps. Okay, so now if I can find that, we have unique analytes, and I'd like to open it up with Excel. And then save it as a CSV file. Comma separated values. Okay. Close that. So let's see, which one is the CSV file? Yes, the top one, and this is a Excel worksheet. So I'm going to delete this one. So now the next time we run SPS on AWS, we will be sure to add this unique analyte file in so that it will assign the same analyte name to any compounds that it sees that have the same mass and about the same mass and retention time. So thank you for watching this video, and I hope that you soon get a chance to try this SPS on AWS.